Hello there, welcome to AQA A-Level Chemistry Support. This is one of many videos. Hopefully you find them useful. If you do, please have a look at the others and let me know what you think. So this video is going to focus on the very first topic of inorganic chemistry. So just a reminder that A-Level Chemistry is split into the three strands. You've got physical chemistry, inorganic chemistry and organic chemistry. And this is the very first AS topic on inorganic chemistry 3.2.1 and is on periodicity. As always, when we're working, when we're revising, we should always look at the spec and have a copy of the specification in front of us so that we can refer and ensure that we are studying the correct content. So a lot of this we've actually seen before in some of our physical topics when we've done bonding, and we've seen some ionization energies already. So what we're going to look at here is classifying elements as S, P, D or F block, which hopefully we've done some of that before. We're then going to look at the trends in the atomic radius. So it's all for period 3 elements. So we're going to look for period 3, trends in radius, trends in ionization energy and trends in melting point. Okay, some of this we've seen before. And we're going to explain those trends in terms of structure and bonding. So if you've done the structure and bonding in detail, which is a physical chemistry topic, which is 3.1.3 bonding, if you've done that in great detail, then you already have a massive head start on this. So we need to be able to explain those trends. So let's have a look at the periodic table. So here I've got a periodic table and I've split it into 4 different colours. And these 4 different colours are going to represent the different blocks of the periodic table. So the blue block is S. So any element over here and over here, this is helium. This element up here would be hydrogen. Sometimes you'll see hydrogen floating over here. That's absolutely fine. Depends on which periodic table you're looking at. And I believe the one that you get from AQA will in fact have hydrogen here. But all the blue elements are classified as S block. And how do we define an S block element? If you were asked to define an S block element, it's because the outermost electron is in the S orbital. So it depends on where your outermost electron. So all of these elements in blue, their outermost electron is in an S orbital. For example, helium 1s2, its outermost electron is the S subshell. It just happens to be over here because it does have that full outer shell, which is classed as one of the noble gases. So just look out for that one there. Helium is in fact an S block element, despite the fact that it appears on this green block here. So it's where the outermost electrons are found. And this green block here, this is our P block. So if you were to do the electron configuration of anything in this green section, you will find that the outermost electron is in a P subshell. And this section in the center here, these are our D block elements. Okay, they're D block. Don't call them transition block because it's not necessarily transition. You'll see that in a second year topic. Okay, so we're going to call these D block elements. So anything that appears in these sections here are D block because their outermost electrons are in the D subshell. And you do have a block down the bottom that we never talk about. He who we shall never talk about. That is the F block. Okay, so you do need to be aware of it, just that any elements down there are the F block, but we don't need to do electron configurations for those. We don't need to talk about the chemistry of the F block. We just know that it exists. So this section down here, these are F block elements. Okay, so we're going to look at the melting points of elements in period 3. So we're going to look at just at period 3. Now, period 3, the elements that we look at are sodium, we've got magnesium. So all I'm doing is looking along period 3. Remember, you do get the periodic table in your exam. Hopefully, as you're looking at this video, you've got a copy of the periodic table in front of you. If you haven't, you will need one later for the questions. So all I'm doing is going along period 3. I'm identifying the elements here. So those are our elements along the period, okay? And we've got argon at the end. Okay, so we don't need to know the exact melting point, so you don't need to quote the values, but you do need to know the trend. So I'm going to point out that argon has the lowest, so I'm just going to give it as a low. Now all of the others will be above argon. Argon does have the lowest boiling point or melting point, and we'll come back to these and explanations in a minute. So we're just going to look at what those values actually are. The highest of the lot is silicon. So that's where our range goes from. It goes from argon and silicon being the highest. Okay. Now, we have a steady increase from sodium to magnesium, aluminium, silicon. So you have a steady increase there. Okay. So from sodium, magnesium, aluminium, silicon, we have a steady increase. Okay. Probably a slightly bigger than expected increase from sodium, magnesium, but we have an increase along here. And we have a sudden drop for phosphorus. Now phosphorus, in fact, I'm going to just drop this one down a little bit just to give me some room to play. We're going to move this down here. Now phosphorus, we have a massive drop from phosphorus. It drops below sodium, but not below argon. Okay, so that's going to come just about here. So it's below sodium, but it's above argon. Sulfur is slightly higher than phosphorus, but it's below, it's slightly above sodium. So I'm going to draw it above sodium and above phosphorus. So you can see that our sodium there lies somewhere between those two. And then we have a sudden drop down to chlorine. Okay, so it appears to be all over the place. Have an increase, a drop, an increase, a drop, and a drop. Now, if you try to memorize this, you're going to find yourself in a little bit of trouble if you try to memorize all of these trends. Okay, we are far better on inorganic chemistry. Yes, there's a fair amount of having to learn stuff and know stuff, but when it comes to inorganic chemistry, if you can understand the trends, then it makes it easier to recognize the patterns and understand them. Okay, so rather than relying on memory, if you're using logic and understanding, it makes it a fair bit more, more straightforward to see what's happening. So now let's look at the structure and bonding then. Well, the bonding in silicon, this one here, is giant covalent. You've seen that in your topic on bonding. This is giant covalent, which means there are many strong covalent bonds holding silicon together, which requires lots of energy to break. Now the bonding in the first three is in fact metallic. Sodium, magnesium, aluminium, they're all metals. That's metallic bonding. So actually, these first three should be quite straightforward to explain that trend. Recall your understanding on metallic lattices. Got a regular arrangement of positive metal ions and a sea of delocalized electrons, electrostatic attraction between the regular arrangement of metal ions and those electrons. Sodium ions will be 1+, magnesium ions will be 2+, aluminium ions will be 3+. The ions from aluminium will also be smaller, so you can talk about the charge density of aluminium being greater. The electrostatic attraction between aluminium ions and its delocalized electrons is going to be much greater than the electrostatic attraction between magnesium ions. So let's just have a look at magnesium ions. If I just was to draw a couple of them in the exam, you would obviously draw an awful lot more. Aluminium will be smaller in size, but greater in charge. There'll be 3+. So these are more attractive. These aluminium ions are more attractive than magnesium ions. They will have stronger electrostatic attractions with their delocalized electrons and hence stronger metallic bonds in aluminium. And likewise, stronger metallic bonds in magnesium compared to sodium. So that's an increase in metallic bonding strength from sodium to magnesium to aluminium. So that's recalling your knowledge from bonding. Right. So before you saw this, you wouldn't necessarily have been expected to know that silicon was above aluminium, but now you do. Okay, so you are expected to know that the covalent bonding in silicon is stronger than the metallic bonding in aluminium. Okay, and your explanation there, you're just going to say that the covalent bonds in silicon require more energy to break than the metallic bonds in aluminium. Therefore, silicon has a higher melting point, and it's a giant covalent structure. Now, moving on to the next section. So you're revising this in kind of 3 sections, if you like. You've got your metallic bonds on the left. You've got your giant covalent in the middle. There's only one. That giant covalent is silicon. And down at this end, we've got simple molecules. Now, argon isn't even a molecule. It's monatomic. So I was hesitant to include that at the start, but we'll talk about that in a minute. So the types of bonds that hold these 1, 2, 3, 4 substances together are the same. These are all going to be non-polar. It will all be van der Waals forces. Now, phosphorus actually exists as P4. Sulfur exists as S8. Chlorine exists as Cl2. And argon exists as Ar, monatomic. Now, if you recall your knowledge on van der Waals, a van der Waals force arises from the random movement of electrons. The random movement of electrons causes a temporary dipole. These temporary dipoles cause induced dipoles on neighbouring molecules, and then we have an interaction, an attraction between the induced dipole and the temporary dipole, and that attraction between those two is your van der Waals force. So in other words, the more electrons you've got, the more random movement, the stronger the van der Waals. Sulfur is the biggest molecule. It has the most electrons. This will have the strongest van der Waals. Therefore, the highest of the 4. There you go, it's the highest of the 4 because it's got more electrons than all of the other 3, which gives it the strongest van der Waals. In a second place is P4. That's the second largest molecule in terms of electrons. If you're not sure, have a look at the periodic table. How many electrons does 1 phosphorus have? How many electrons does 4 have? So it's got more electrons than Cl2, but not as many electrons as S8. Therefore, that comes a close second when it comes to melting point, boiling point, because it's the second biggest molecule, or the second largest number of electrons, which would give rise to weaker van der Waals than S8, but stronger van der Waals than Cl2 because of the number of electrons it has. And as you can then see, Cl2 comes in third, and then argon comes last. Okay, so these are all to do with van der Waals, simple molecules. Silicon, giant covalent, and the first 3, metallic. We do need to know the relative order though, so we do need to know that, okay? You don't need to know the numerical values, but you do need to know the order. So be careful. Sodium annoyingly needs to fit between phosphorus and sulfur, so be careful when you're plotting that there, okay? Silicon must be the highest. Argon, chlorine, phosphorus are the 3 lowest. And then be prepared to talk about the bonding in each of them, the structure and the bonding. Giant metallic for the first 3, giant covalent for silicon, and simple molecules van der Waals for the next 4, non-polar van der Waals. Okay, let's have a look then at the trend in first ionisation energy across period 3. Now we've definitely done this in an earlier topic when we've looked at ionisation energies in physical chemistry. So this should just be revision. You should be fairly comfortable with this. So we've got sodium, again, identify my elements, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Now the general trend across a period, the general trend is an increase in ionisation energy because there is a decrease in radius, there is an increase in nuclear charge, while the shielding remains fairly similar. So those are our 3 things to consider. The shielding, its nuclear charge, and its radius. So we're using those three factors. So there is a steady increase, okay? The highest is argon, put it here. The lowest is sodium. And there is a general increase. But remember, we do have a blip. So it increases from sodium to magnesium, but we do have a drop as we come across to aluminium, and then silicon is back up again. Be careful when you draw this blip. You can't draw aluminium below sodium. And likewise, you can't draw silicon below magnesium, okay? And then we have another increase to phosphorus, but then you have a drop again to sulfur, and the increase back up to chlorine. So you kind of have two anomalies, really. It's that aluminium, sulfur. You might want to pause the video now and have a little think about why those anomalies exist, because I am going to explain that. So we have an increase, decrease, increase, increase, decrease, increase, increase. The general trend is an increase. That is your general trend. But you do have some anomalies. So explaining the general trend, I did it at the beginning, but I'll do it again, because as you go across the period, the radius decreases. The nuclear charge increases. That's the number of protons. The proton number is increasing, and the shielding remains about the same. Okay, so it's about the same. This means that the outer electron is more strongly attracted to the nucleus and more energy is needed to remove it. That's the general trend. So now let's explain why we have this blip. You may wish to pause the video to see if you can remember why you have this blip. But we have this blip here because this is a new subshell. So the aluminium, we've got a new subshell, which is the P subshell. So it's a new P subshell, which is higher in energy and more easy to remove. So this is to do with the evidence of the subshells. What's happening with sulfur? Well, sulfur, this was to do with electron pair repulsion. In sulfur, you had 4 electrons in your P subshell, and this 4th electron that's been removed is easier than expected because it is repelled by this electron that's been forced to pair with. So it's slightly easier than expected due to electron pair repulsion. So hopefully that's just a revision of earlier topics. It's worth mentioning electronegativity trend at this point, even though it didn't appear in the spec at the start there. We do need to know the trend in electronegativity from previous and other topics. So let's just remind ourselves of what electronegativity is. A definition for that would be ability an atom has to attract a pair of electrons in a covalent bond. So it's all about that covalent bond. You've got a shared pair of electrons between 2 atoms. If one of those atoms is more electronegative, it attracts the electrons towards itself. So it's a measure of the ability an atom has to attract the bonding pair of electrons in a covalent bond. So what affects the electronegativity then? It's the same factors: the nuclear charge, the shielding, and the radius. So if you've got a smaller radius and a bigger nuclear charge, you are going to be more electronegative. So the trend in electronegativity is electronegativity increases across the period. There are no exceptions here. Right? As we go across the period, the radius decreases, the nuclear charge increases, the shielding remains similar. Therefore, the most electronegative in period is chlorine. You may ask yourself, why have I identified chlorine and not argon? So why did I identify chlorine as the most electronegative and not argon? Maybe have a think about that and pause the video. The reason I've said chlorine and not argon, because actually argon does have a smaller radius, it does have a bigger nuclear charge, and the shielding is similar. But the reason I'm saying chlorine is because by definition, electronegativity is the ability an atom has to attract the bonding pair of electrons in a covalent bond. Argon will not form covalent bonds, therefore we can't measure its electronegativity because it won't form covalent bonds because it already has a full outer shell. So chlorine is the most electronegative in period 3. Okay, time for you to pause the video and have a look at these multiple choice. I'm going to give the answers out in the next few seconds. So pause the video, and when you're ready to go through them, press play. Highest first ionisation here. Hopefully, don't really need to explain this one at all. Your answer here is B. Okay, so you should know the trend there, and that phosphorus out of those four elements has the highest first ionisation energy. Be prepared to explain it as well if this wasn't a multiple choice. 2. Which of the following is the correct statement about the trend in atomic radius across period 3? Well, the radius definitely decreases, so we know it's not A or C. And then we're looking for the explanation. Radius decreases because shielding decreases. Well, no, it doesn't. Shielding remains similar. It decreases because the nuclear charge increases. The answer here is B. Question 3. Which of the elements are shown in increasing order of the stated property? So I'm going to give you the answer here. The answer is D. Hopefully you can see the explanations for that. I'm not going to go through each one. That's going to take too long to go through those three. If you do need some help on that, then please ask. I'm happy to explain that if you need to. Okay, question 4. Which of these elements has the highest second ionization energy? Be careful there, okay? Because if it was first or second, it would be massively different, okay? Because actually, if it was first ionization energy, you would probably be picking argon. However, it's the highest second ionization energy, and the answer here is sodium, because once you've removed the first electron, you are now in a whole new shell, which has significantly less shielding and a much smaller radius. So if you're unsure of these types of questions, what I suggest you do is you actually give the full electron configuration of each of them, take away one electron, and then look at the second electron that's going to be removed, okay? Because it's the second electron that you're removing here, not the first and second, just the second. Okay, 4 more questions then. I suggest, again, you pause the video, you have a look through these, and I'm going to give you the answers as soon as you unpause the video. So which is the F block? Hopefully this is dead straightforward, only if you have a periodic table in front of you, of course. It's probably worth pointing that out. You do need a periodic table, because if you don't, you might find this difficult. But with a periodic table, this is dead straightforward. And question 6, highest melting point out of those from that list, we are going to identify, well, silicon's not in there. The second highest after that is aluminium. So if silicon was there, it would have been silicon. It's not. Aluminium is the second. Next, which is the correct order for melting points of period 3? So another melting point 1. Phosphorus, let's have a look. And your answer here. It's going to take a little bit of working out, I think. I'm not going to explain it because you do just need to know them, I guess, once it comes to those melting points. The correct answer here is C. And finally, which is the correct classification for yttrium? So you need to find this in the periodic table. You will find that yttrium is in fact in the D block. It's a D block element. Finally, again, last multiple choice now before we look at some written exam questions. So question 9, which element is in the D block? Again, with a periodic table in front of you, this should be fairly straightforward. This one here is in the D block. Okay then, a written question here. 7 marks, so this should take you in the region of 7 minutes, maybe 7, 8, 9 minutes. So pause the video. If you want to time yourself, time yourself. If you're just quite happy that you want to work through your own leisure, then that's fine. But pause the video, and when you're ready, unpause it. We'll go through this. Okay, deduce which of Na plus or Mg2 plus is the smaller ion. If you were to look at the electron configuration of them both, they both have the same electron configuration. which means they have the same number of shells. However, magnesium has a higher nuclear charge, which means the outer electrons are pulled more closely, so the smaller ion is Mg2+. And my explanation is both have the same electron configuration. However, magnesium has more protons, a bigger nuclear charge, and will pull the electrons closer, therefore smaller radius. Write an equation to represent the process that occurs when the first ionization energy of sodium is measured. First ionization energy is going from gaseous, state symbols are essential here, to gaseous 1+ ions. That is the only accepted answer. There is nothing else that's accepted there. See, the first ionization energies of some period 3 elements are shown in the following graph. There we go. Complete the graph by plotting approximate first ionization values for magnesium and sulfur. So magnesium and sulfur, right. We know that magnesium is going to be above sodium and it's going to be above aluminium. So there's a temptation here to put it there for the general trend, but no, we know that there is a blip, so it has to be above this value but below this value. Okay, so it has to come in this range here. Anywhere in that range there is correct. 1 mark. And then we're asked to put in sulfur. Again, the temptation would be to put it somewhere here, but that's wrong because sulfur has a drop from phosphorus due to the electron pair repulsion. So again, we're looking for any region between those dotted lines there. And I've explained it. Okay, so an explanation why the first ionization energy of sulfur is different from phosphorus. So I'm saying that the first ionization energy of sulfur is less than the first ionization energy of phosphorus, and that's because due to electron pair repulsion, the electron being removed is paired in a p subshell and undergoes electron pair repulsion, which means less energy is needed than expected to remove that electron. Next question then, 4 marks, so this should take about 4 minutes. Okay, so pause, and if you want to time yourself, go ahead, and then unpause when you're ready for the answers. Right, A, explain why the atomic radii of the elements decrease across period 3 from sodium to chlorine. So the reason that we have a decrease in radius is because they have the same number of shells, so we have the same number of electron shells, but we have a bigger nuclear charge, which means the nucleus pulls those shells closer to the nucleus and therefore a smaller radius. Explain why the melting point of sulfur is greater than that of phosphorus. So we're going to identify first of all that the forces of attraction between sulfur and phosphorus are both van der Waals. However, sulfur will have greater van der Waals because sulfur is a bigger molecule with more electrons, will have stronger van der Waals forces. Next question. 7 marks here, approximately 7 minutes. Pause the video, and when you're ready, we'll go through. Right. A. State and explain the element in period 3 that has the highest melting point. The element here is silicon, and we're explaining it. We're going to identify the structure, which is giant covalent. I'm going to explain that giant covalent, melting a giant covalent structure requires breaking many strong covalent bonds. B. State the element in period 3 that has the highest first ionization energy and explain your answer. So we're going to identify argon, and that's because they all have similar shielding. However, argon has the highest nuclear charge and the smallest radius, which has the strongest attraction with the outer electrons. Therefore, more energy would be needed to remove the outer electron. And finally, C, the element that has the highest electronegativity value. Remember, we can't say argon here because argon won't form covalent bonds, so we're identifying this element as chlorine. Hopefully then that was useful. So look out for the next video coming on inorganic chemistry, which will focus on group 2. So please let me know what you think.